Hi everyone, welcome back to chemistry. In the last couple videos we talked about different ways that we can classify matter, and in this video I want to talk about different ways that we can measure matter using different tools. So on the right there you see some examples of some tools you can use to measure matter in different ways. So you can measure length using a ruler. You can measure the mass using like a balance or a scale like this. You can measure the volume using a graduated cylinder over here or a beaker here. But units are really important. So anytime you report a measurement, so some measured value, you always want to include a unit. So over here we've got 5.2 kilometers. Kilometers is our unit and 5.2 is our number. So anytime you report these measurements, you need both of those things. It's really important. So I always like to give the example of, like, say you're going on a walk with your friend and you text your friend and you're like, hey, how long is the walk today? And your friend just says 5.2. It's like, well, 5.2 what? 5.2 miles? That's a really long walk. Or is it 5.2 minutes? That's a pretty short walk. So we always want to report our units. Units are so important that scientists have decided on an international system of units, or SI units, named after or abbreviated after the French translation. So the idea behind international system of units, or SI units, is that we used to come together and communicate with other scientists, and we would share our findings, and our findings would often be kind of confusing because we'd all be using different units. So really important to use similar units so that we can communicate effectively with each other and kind of compare apples to apples. So examples of some base units, which are the kind of fundamental units of SI, is these here. So we've got the thing that you're actually measuring is over on the left, and the unit you're going to use to express that measurement is on the right. So if you're measuring length, you're going to measure in meters. If you are measuring mass, you're going to report your number in kilograms, time in seconds, amount in something called moles, which we're going to talk about in the future, temperature in Kelvin, which we'll also talk about in the future, and volume in liters. So some of these you might be familiar with, and some of them you might not. In science, we always use the metric system. That's the preferred unit of measurement. And the reason for that is that it's really easy to convert between smaller and larger units in the metric system. Whereas if you're using the English system, or sometimes referred to as the imperial system, that's inches or pounds or ounces. That's a lot more tricky. So we use the metric system in science. Sometimes we will use the SI system, okay, when we're reporting our findings. And sometimes we'll kind of deviate a little bit, but we'll still use metric. So for instance, even though mass is measured in kilograms using the SI units, in chemistry, we often measure mass using grams. And the reason for that is that in chemistry, we're usually measuring small amounts of substances, whereas in other sciences, they're usually dealing with larger objects. So they're going to want to use a larger unit like kilograms. So there are also these things called derived units. And that's kind of a fancy way of saying that just like you can multiply and divide numbers, right? You can also multiply and divide units. So what do I mean by that? If you look at this equation down here for density, it says density equals mass over volume. So let's break this down for a second. So in terms of finding the density, usually when we're trying to find the density of something, we're looking at a specific object and we're saying, okay, what's the mass of that object, right? And what's the volume of that object? And if we know those two things about the object, we can figure out what the density is. Okay, and just like any other algebraic equation, because remember, this is an equation. This is an algebraic equation. So you can also see it written like this, and that might look more like an equation to you, but it's an equation. So anytime you have an algebraic equation with 3 variables, and you know 2 of those variables, you can solve for your unknown. So plug in the numbers you know, and then solve for the one that you don't know using algebra. So let's practice that a little bit here. So for this one, the the top one says a regular object measures 4 centimeters by 3 centimeters by 2 centimeters. What is the volume of the object? So remember, when the volume of a rectangle is equal to length times width times height. So if we have, our rectangle here, and we know each of the dimensions of our rectangle, we can solve for the volume of that object or of that rectangle. So let's go ahead and plug that in. Whoops. And let's just, I don't know, make it easy on ourselves, and we'll do 4 centimeters times 3 centimeters times 2 centimeters. And that's going to equal, and remember, when you multiply these different measurements out, you're not only multiplying the numbers, right? So I did that and I multiplied the numbers, but you're also multiplying the units. What is centimeters times centimeters times centimeters? Yeah, it's going to be centimeters cubed. Okay, so centimeters cubed. That is a unit of volume. So notice, really important that you keep the units when you're doing your calculation. Okay, I didn't remove them in this step here. And the reason for that, and I know it's tempting just to go 4 times 3 times 2. Okay, I know that's 24. But the reason that you want to keep the units is that it's a really good check for when you, to make sure that you got the right final answer. So if you ended up with a volume, you were looking for the volume of your object, right? And you ended up with just centimeters. Is that a unit of volume? No, what's centimeters a unit of? Yeah, centimeters is a unit of length, right? So that's not what you want to end up in. So this is a really good way to kind of double check that you're on the right track. All right, so the density of an object, oops, get back to blue here. The density of the object is 0.35 grams per centimeters cubed. What's the mass of the object? All right, so notice that they reported the density in units of grams per centimeters cubed. This is not typical for liquids. For liquids, we usually report the density in grams per mil. But for solids, something like that solid rectangle that we have here, we usually report our density in grams per cm cubed. Centimeters cubed, I should say, or cubic centimeters, and that's for solids. And the reason for that is that for liquids, it's easy to measure in milliliters, and that's because we're going to use something like this up here, a graduated cylinder or a beaker, and it's going to read out how many liters we have, or milliliters. So that's easy for liquids. And then for solids, if I try to put that solid rectangle into a beaker and measure how much volume it takes up, I'm not going to be very successful, right? So that's the reason that we report our answer in grams per centimeters cubed for solids, usually. But I'll always ask for the units that I want, and then your job is to try to get your answer to be in those units, right? All right, so the density of the object, so we know the density. So let's go ahead and write our density equation. So density equals mass over volume. So we just solved for the volume of our rectangular object, right? That's here. So we'll plug that in over here, and we've got that. That kind of looks like a V, but we'll know the volume. We know the density, right? That's given to us right here. So we can plug that in as well. And then we can solve for m, which is our unknown. So let's go ahead and solve for m now, and that way we can just plug in our numbers and go. So let's do, in order to get m alone, right, we want to solve for m. So when I say that, that means that I want to get m alone. So what do we want to do? We want to do the opposite of division, which is multiplication, in order to get rid of that v on the bottom. So, and then we can cancel that out, right? Multiplying v times m over v is going to cancel out those volumes, okay? But whatever we do to the right side, remember, it's an equation. We have to do the same thing to the left. right? These sides, these two sides of the equation, they need to be equal. And if I only multiply by volume on one side and I don't do it to the other side, those two sides are no longer equal. All right, so now we've got VD equals M. And we are good to go, right? We wanted M to be alone. I'm going to kind of rearrange this so that it's just M is on the left. That's kind of just the way my brain likes to see it. But if you are okay solving it in this form, that's great. Okay, so M equals, now let's plug in our values. So V we have up here is 24 cm cubed. Remember, I'm writing the units, okay? And then D we have here, that is 0.35 grams per centimeter cubed. Whoops, that's a weird looking arrow. Okay, so notice, remember, for our derived units, we have some unit over something else. It's kind of like when you measure in miles per hour. So in the United States, right, we measure in miles per hour. But if you ever drive up to Canada, you'll see on the speed limit signs that they measure in kilometers per hour. So different types of measurement or different types of units, but the same idea, both derived units. You're dividing miles by hours, right? Kilometers by hours. All right, so I've got grams per centimeter cubed. And just as a side note, if you wanted to write this out, this is just a fraction, right? Or it's grams divided by centimeters cubed. So you could also see it written like this. That's the same thing, right? It's the same exact thing. You're taking your grams and you're dividing by centimeters cubed. Okay. All right, so notice, and in fact, I'm actually going to write it like that. Grams per cm cubed. All right, so notice, centimeters cubed is in the numerator here. What do I mean by that? Remember, there's an imaginary 1 down here. Okay, so this number is in the numerator, and so are those units. Okay, if centimeters cubed is in the numerator and the denominator, what happens to it? Yeah, it gets canceled out. So we can cancel that out. I'm going to go ahead and clean this up just so we can see a little better. Maybe clean that up and that up. All right. And now we're left with M equals 24 times 0.35. 24 times 0.35. And that's going to give me 8.4. Is this my final answer? Am I done? No, what do I have left? Grams, this pesky little grams hanging out up there. Now, why is that important? Well, what am I solving for? The mass of my object. What do we measure mass in? Yeah, grams. All right, so the coolest thing about the metric system is that you can add these different prefixes in front of your base units. So base units are things like, the base things that you measure your different properties of your matter in. So you can measure, right, the mass. Whoops. So you can measure the mass in grams, right? So grams is a base unit, liters, meters, seconds, right? These are all examples of base units. So the way that base units work and why we like to measure in the metric system so much in science is that when you add one of these prefixes to your base unit, so you're going to put, kilo in front of grams and you're going to get kilograms. You're going to put centi in front of meters and you're going to get centimeters. You're going to put milli in front of seconds and you're going to get milliseconds. Stuff like that. When you add one of those prefixes in front of your base unit, you're actually changing the size of that unit. Okay, so what I like to do when I look at this table here is I like to kind of break it up a little bit because it's a lot of information thrown at us at once. So what I like to do is I like to draw a little line right under kilo. I like to separate the prefixes that increase the size of my base unit and the prefixes that decrease the size of my base unit. So what do I mean by that? So if we go up this way, on this chart, we are getting bigger than our base unit. Okay, those are bigger units. So kilograms are larger than grams. And then as we go down this way, from deci down to pico, we're getting smaller than our base unit. Okay, so decimeters are smaller than meters. Centimeters are smaller than meters. Millimeters are smaller than meters, right? All of those units that I've drawn the arrow, the down arrow for, those are getting smaller than your base unit. You might be sitting there asking, well, like, how much bigger are the bigger units and how much smaller are the smaller units? That's given by this column right here that shows the multiplier, which are these 10 to the something, right? These multipliers here, that you multiply by your base unit to either increase the size of your unit or decrease it. Okay, so that tells you how much bigger or smaller that unit is when you add the prefix. Okay, so again, I know kind of confusing. So let's take an example here. So for example, say I wanted to convert, 5 grams to kilograms, because I guess I'm trying to use SI units for mass, which is the kilogram, right? And I measured everything out in lab in grams. So I want to convert from grams to kilograms. Well, if I have 5 grams and I want to get to kilograms, grams is my base unit, right? So I'm gonna highlight grams in yellow. So grams is my base unit. And then I know I'm trying to get to kilograms, so we'll make kilograms blue. So if I'm trying to get to kilograms and I'm in grams, what I want to do is I want to multiply my base unit here using this chart by 10 to the third, because that's the multiplier. That's how much bigger kilograms are than grams. They're 10 to the third bigger than grams. So let's take a little side quest and think about 10 to the third. What is 10 to the third? It might have been a while since you've used exponents, and that's totally okay. So what I really want to do right now is I want to convince you that 10 to the third equals 10 times 10 times 10. Why does 10 to the third equal 10 times 10 times 10? Yeah, because this 3 is telling us how many times we want to multiply this number here, and it doesn't always have to be 10. When you're doing, different math equations, it might be a different number, but for our purposes here, for the metric system, it's always going to be a factor of 10. Okay, but that 3 is telling you I need to multiply 10 by itself 3 times. Okay, so whatever number's there is how many times you're going to multiply that other number by itself. So in this case, we've got 10 times 10 times 10 is 10 to the third. What is 10 times 10 times 10? Yeah, it's 1,000. If you don't believe me, look it up or type it into your calculator and make sure that you get the same answer. That's totally fine. But 10 to the third equals 1,000. So this is all the same number. These are all numbers, right? They're just represented in a different way. Okay. So 10 to the 6, right? 10 to the 6 just above that is 10 times 10 times 10 times 10 times 10 times 10. Is that 6? Yeah. Which is what? Yeah, 1,000,000. So what you'll notice is that when you have 10 to some number here, the amount of zeros is equal to, after your 1, is equal to the exponent that you have written there. Okay, so 10 to the third is equal to 1,000. That's 3 zeros because it's 10 to the third, 3 zeros. 10 to the 6 is going to be 1,000,000 with 6 zeros because we're 10 to the 6. Okay, now when you look at this, you might also be looking over here at these negative, and let me clean this up a little bit, at these negative exponents. What do negative exponents mean about our units? Are those, yeah, they're smaller. So when you have those negative exponents, you can actually express something like 10 to the 2, and let me actually zoom in a little bit here. 10 to the 2 is actually 1 over 100. What you're doing is you're dividing 10 by itself twice, 2 times, right? If you're 10 to the negative 3, you're going to divide 10 by itself 3 times, which is the same thing as 1 over 1,000. 10 to the negative 6, divide 10 by itself 6 times, and you're going to get 1 over 1 million. So notice, okay, 10, just looking at 10 to the negative 3 versus 10 to the positive 3, notice the difference in these numbers. And I'm not going to like explain it, but just think about it in your head for a second. What are you noticing about those numbers? Okay. All right. So as we work through lots of problems with this, I promise it'll get a lot easier. I know it's a lot to learn at first. Just stay positive, keep working on it, practice, 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 and it'll get a lot easier. I do want to let you know which ones you need to memorize for this class, because I don't want you to memorize every single one of these. So the ones I want you to memorize for this class are kilo, deci, centi, milli, and micro. And when I say you need to memorize them, I want you to memorize the prefix. So what are you going to write in front of your base unit? I want you to memorize the abbreviation, okay? And I want you to memorize what number you need to multiply your base unit by to convert to that unit. Okay. Real quick side note, this letter, you might not have seen it before. That's the Greek letter mu. Mu, so kind of like a cat almost. And it's kind of weird. It's like you basically draw a U shape with kind of like a line in front. Okay, so watch me draw that here for a little bit. And I'm not the best at drawing it, but something like that. Almost looks kind of like a cursive M as well. Okay, so that's the Greek letter mu, and it's used to represent micrometers. If you put M in front of, I don't know, G, milligrams, and you're trying to say that you have micrograms, I'm going to mark this wrong. Because what is mg? Yeah, that's milligrams. If you want to say you have micrograms, you need to do that little mu. Okay. All right, so let's go ahead and identify the larger unit in each of the following, just to get more of a sense of how big these units are in comparison to each other. So millimeters or centimeters, which one's larger? Pause the video, think about it, and then come back. Which one's larger? Well, centimeters are larger than millimeters. Why is that? Let's take a look at our chart. I said as we go down this way on this chart, we're getting smaller and smaller. So centi is above milli. Let me just clean this up so we have a little bit more. We can see this a little better. Centi is above milli. So centimeters are going to be larger than millimeters. Okay, so centimeters are larger. What about kilograms versus centigrams? Yeah, kilograms, a lot larger actually. So let's look at kilograms here. So kilograms are up here and centigrams are down here. So kilograms are a lot larger than even just our base unit, and centigrams are really small, so much, much larger for kilograms. What about milliliters, or what's this one? Yeah, that one's microliters. So milliliters are smaller than microliters are smaller than milliliters. All right, and then this one, this is actually another way of representing microliters. So these two are the same thing, microliters. So sometimes instead of the mu symbol, you can also see MC. That's very common in healthcare fields to see MC. So MC in front of, liters is microliters. MC in front of G is micrograms, stuff like that. All right, so which one is bigger, microliters or kiloliters? Yeah, kiloliters are larger. So what I do want to stress is that these abbreviations, it really matters whether you're capitalizing the letters or leaving them in lowercase, okay? If you put big M for milligrams, you're not representing milligrams, you're representing micrograms. So just be careful with things like that, okay?